So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CAIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. So today we are going to start section 3.4, sound. Sound waves are produced by vibrating sources. When something vibrates, it produces sound waves. And since it is produced by vibrations, sound is a longitudinal wave. When a sound comes in contact with a solid, those vibrations can be transferred to the solid molecules, hence it can travel. For example, sound waves can cause a drinking glass to vibrate. But if the glass vibrates too much, means if the frequency is too high, the movement can cause the glass to shatter. Human ears can only hear the sound with the frequencies from about 20 Hz to 20,000 Hz. But as the age progresses, the upper limit, means the range of 20,000 Hz, decreases. Sound waves require a medium to travel through. If there are no molecules, for example in vacuum, sound cannot travel. So all those movies of Star Wars where the planes are shooting at each other in space and you can hear the lasers going beep beep beep, shoom shoom, they are actually scientifically false. In space you cannot hear a single sound. Speed of sound in air. Sound waves travel at a speed of about 340 meters per second in air at room temperature. The higher the temperature, the greater the speed of sound, because due to increase in temperature, air molecules would already be in motion, so sound would travel faster. The speed of sound in air varies from 330 to 350 meters per second. In different objects, sound travel differently. The speed of sound is greatest in solid, then liquid, and then the gases. This is a little table to show you the comparison. As you can see, a solid is having the highest speed, that is 6,420 meters per second, whereas a gas, sulfur dioxide, has the lowest speed, that is simply just 213 meters per second. Sound travels at different speed in different mediums, the fastest in solid and the slowest in gases. Measuring the speed of sound. There are several experiments that can be carried out to do this. 3 methods are described below. The method 1, measuring sound between 2 points. Two people stand a distance of around 100 meters apart. The distance between them is measured using a trundle wheel. One person has two wooden blocks which they clap together above their head. The second person has a stopwatch which they start when they see the first person clapping the blocks and stop when they hear the sound. This is then repeated several times and an average value is taken for the time. The speed of sound can then be calculated by using the formula speed equals to distance upon time. In this case, distance would be 100 meters and time would be whatever average value of time you get from the stopwatch. Method 2, using echoes. A person stands about 50 meters away from a wall or a cliff using a trundle wheel to measure this distance. The person claps two wooden blocks together and listens for the echo, whatever you want to call it. A second person has a stopwatch and starts timing when they hear one of the claps and stop timing when they hear the echo. The process is then repeated 20 times and an average value is calculated. The distance traveled by the sound between each clap and echo will be 2 multiplied by 50, because an echo basically means sound traveled from the source till the wall and then it was reflected and it came back, means it had to travel twice the distance. The speed of sound can be calculated by using the formula sound equals to distance multiplied by 2 divided by time taken. Third method is by using an oscilloscope. Oscilloscope will be discussed in detail in section 4. Two microphones are connected to an oscilloscope and placed about 5 meters apart using a tape measure. The oscilloscope is set up so that it triggers when the first microphone detects a sound, and the time base is adjusted so that the sound arriving at both microphones can be seen on the screen. Two wooden blocks are used to make a large clap next to the first microphone. The oscilloscope is then used to determine the time at which the clap reaches each microphone and the time difference between them. This is repeated several times and an average time difference is calculated. Then we can use the formula speed equals to distance between microphones divided by time taken between peaks. Now sounds generally have two qualities. One is known as a pitch and one is known as a loudness. The frequency of a sound wave is related to its pitch. Sound with a higher pitch have high frequency, means if a sound wave has greater frequency it will have a higher pitch, whereas if a sound wave has low frequency it will have a lower pitch or a longer wavelength. The amplitude of a sound wave is related to its volume. Sound wave with a larger amplitude means a high volume or loud sound, whereas sound with a small amplitude means a less loud sound or a soft sound. Echoes are the sound waves that are reflected off hard surfaces. The reflection of a sound wave is called an echo. Echoes can be used to measure depth or to detect objects underwater by using sonars. A sound wave can be transmitted from the surface of the water. The sound wave is reflected off the bottom of the ocean. The time it takes for the sound wave to return is used to calculate the depth of the water. The distance the wave travels is twice the depth of the ocean. This is the distance to the ocean floor plus the distance for the wave to return. Then we have something that is known as ultrasound. It is the name given to the sound waves with a frequency of more than 20,000 Hertz. When ultrasound reaches a boundary, some of the waves are partially reflected. The remainder of the waves continue through the material and are transmitted to that medium. Ultrasound transducers or devices are able to emit ultrasound and receive ultrasound at the same time. The time taken for the reflection to reach a detector can be used to determine how far away a boundary is. This is because ultrasound travels at different speed through different media. This is by using the speed distance time equation. Speed equals to distance upon time. This allows ultrasound waves to be used for both medical and industrial imaging. In medicine, ultrasound can be used to construct an image of fetus in womb, to generate 2D images of organs and other internal structures, as long as they are not surrounded by bone, as a medical treatment such as removing kidney stones. An ultrasound detector is made up of a transducer that produces and detects a beam of ultrasound waves into the body. The ultrasound waves are reflected back by boundaries between tissue in paths of the beam. For example, the boundary between fluid and soft tissue, or tissue and bone. When these echoes hit the transducer, they generate electrical signals that are sent to the ultrasound scanner. Using the speed of sound and the time of each echo's return, the detector can calculate the distance from the transducer to the tissue. By taking a series of ultrasound measurements sweeping across an area, time measurements may be used to build up an image. Unlike many other medical imaging techniques, ultrasound is non-invasive and is believed to be safe or harmless. They can be used to construct an image of fetus in womb. In industries, ultrasound can be used to check for cracks inside metal objects or to generate images beneath the surface. A crack in a metal block will cause some wave to reflect earlier than the rest, so this will show up as pulses on an oscilloscope trace. Each pulse represents each time the wave crosses a boundary. The speed of wave is constant, so measuring time between emission and detection can allow the distance from the source to be calculated. Now let's have a look at an example question. The sound from a ship is reflected by a cliff. An echo is heard by a sailor on the ship 4 seconds after the sound is made. The speed of sound is 320 meters per second. How far from the cliff is the ship? Now remember that when we are talking about echoes, then distance is twice or 2x. Over here it takes 4 seconds for the sound to return. That means the actual distance or the actual time taken from the ship to the cliff would be 2 seconds. The other 2 seconds, or the other half of the time, is taken for the sound wave to travel from the cliff towards the ship. So we apply the formula distance upon time. We know speed, will simply multiply it with the time. Speed equals to distance upon time, so we'll keep distance on the right hand side and will multiply time, that is 2 seconds, with the speed. So we'll get the answer as 640 meters. That would be B. Figure is the trace on the screen of the oscilloscope. Describe and explain how the trace on the screen changes as the pitch of the sound becomes higher. We have already studied when the pitch becomes higher, the frequencies increase. So we'll see more peaks or more waves. Thus more waves would be seen on screen. That's it. This is all you need to know for section 3.4, and we have officially wrapped up our section 3 waves. I'll see you guys in the next lecture. If you have any problems, feel free to comment below and I'll make sure to reply you. And I'll see you guys in the next video. Take care. Allah Hafiz.